This video, we solve problem 6.1.12 from Nagle's Fundamentals of Differential Equations, 7th edition. This problem was featured on the quiz number 4 in the Differential Equations class at TCC, Tulsa Community College, in the spring 2021 semester. You were asked to determine whether the given functions are linearly dependent or linearly independent on the specified interval and justify your decision. We've got this cosine function, this cosine squared, and sine squared. Now, if you are like me, hopefully you're seeing that and you're like, oh, actually, I remember a relationship between these functions because we've got power reducing formulas that we use in Calculus 2. We use them pretty often in order to write cosine squared and sine squared in terms of cosine of 2x. And what that means is that these are linearly dependent. There is a combination of these two functions that I could use to get this function back. Or there's a combination of these two functions that I could use to get this function. And so just knowing what we know about linear independence or linear dependence. Linearly dependent sets include functions that are sort of redundant. That function could be found through a combination of the other functions. And in this case, there's some redundancy here. So these are linearly dependent functions just because of what I know about trig identities. But let's verify it a couple of ways. First, we're going to use the Wronskian to compute we'll compute the Wronskian of these and see if the Wronskian is 0. Because I suspect that they're a linearly dependent set because I know those trig identities that relate these functions, I will say the Wronskian should be 0 because I know it's a linearly dependent set. If I don't get 0, I know I've done something wrong, or perhaps I'm remembering my trig identities incorrectly. So let's compute the Wronskian, and then let's talk about answering this question the way MyLab Math is expecting us to answer it. Because in MyLab Math, they weren't actually expecting you to compute the Wronskian at all. So remember how the Wronskian works. It's a 3x3 determinant. You're going to put this first function in the first row and first column entry, and then you're going to take its derivative twice. The derivative of 5 times cosine of 2x is 5 times the derivative of cosine of 2x. Derivative of cosine is negative sine. The angle stays the same, and then we multiply by the derivative of the inside. So we're going to take this, we're going to multiply by 2, and then we're also going to multiply by that 5, so we'll have a negative 10 there. And then when we take the derivative again, we're going to bring this constant down, negative 10, times the derivative of sine of 2x. Derivative of sine of 2x is cosine of the same angle times the derivative of the inside. Well, the derivative of 2x is just 2, so we're going to take that 2 and we're going to multiply it by our constant, so we're going to have a negative 20 there. Okay, so that's what we have in the first column. In the second column, we've got cosine squared x and its derivatives. I'm going to do a little bit of side work, or scratch work here. Remember, cosine squared x is really just cosine of x, quantity squared. So when I'm taking the derivative of this, I'm thinking of it this way. I've got a function nested inside another function, so I have to use the chain rule. According to the chain rule, the derivative of a function squared is 2 times that function. Put your inside function back inside, and then multiply by the derivative of the inside. And the derivative of cosine of x is negative sine of x. And so we have negative 2, and I like to put sine of x first, sine of x, cosine of x. Now you can leave it like this if you want to, or if you remember a trig identity, you can use that here. It turns out that 2 times sine of x times cosine of x is actually sine of 2x. There's an identity that says that that's true. So if you want to, you could substitute, oops, the 2's gone, sine of 2x there, or you could just use this. But I think I'll use the negative sine of 2x here because it makes it easier to compute the derivative. The derivative of sine is cosine, so I bring my negative down, cosine of the same angle times the derivative of the inside, which is 2. Okay, and then we're going to do something similar for sine of x. I bet you can tell what's going to happen here. We're doing the same thing. We've got a sine function inside a squaring function. That's what sine squared x means. It really means sine of x squared. The derivative of sine of x squared is derivative of the outside, so that's 2 times the original function times the derivative of the inside, and the derivative of sine of x is just cosine of x. So we've got sine of x times cosine of x times 2, which we know is sine of 2x. So I'm going to use that. But you could, if you want, use sine of 2 times sine of x times cosine of x, and that will work as well. And the derivative of sine of 2x is cosine of 2x times the derivative of the inside, which is just a 2. All right. So now we will evaluate this 2 by 2 or 3 by 3 determinant by writing it in terms of 2 by 2 determinants. And you can do it in any way you want. I would recommend expanding along the first row. Usually we want to expand along a row or a column that has a bunch of zeros in it, but we don't have any. So I'll just use the first one. So we'll have positive 5 times cosine of 2x times the 2 by 2 determinant that comes from crossing out the row and column containing that entry there. So we're going to evaluate that. And then we'll say minus cosine squared of x times the 2 by 2 determinant that crosses out the row and column containing the cosine squared, plus sine squared x times the 2 by 2 determinant that comes from crossing out that row and that column. So we end up down here with something that looks like this: 5 times cosine of 2x times this 2 by 2 determinant. Now you do not have to write this down if you don't want to. I am just showing my steps for those people that need it. Not everybody needs this step. It's okay if you do, and it's okay if you don't. No judgment here. And we have minus cosine squared x times the 2 by 2 that comes from crossing out that row and that column. We've got negative 10 sine of 2x, negative 20 cosine of 2x, sine of 2x, and cosine, or 2 cosine of 2x, plus sine squared x times the 2 by 2 that comes from crossing out that row and that column, that 2 by 2 determinant. Okay, so one way to justify our answer is to compute the Wronskian, and if we get 0, we know these functions are linearly dependent. If we don't get 0, then we know that they're independent. So linearly independent, at least on the entire real line. There might be some particular x values where they're linearly dependent. So we have 5 times cosine of 2x times this. Now remember how 2 by 2 determinants work. We multiply across this diagonal, multiply across that diagonal, and subtract. So we're going to have negative 2 times sine of 2x times cosine of 2x minus a negative 2, so it's going to be plus 2 times sine of 2x times cosine of 2x. Isn't that nice? You see it? They're exactly the same, but with opposite signs. So those are gone. And this whole factor here is 0. So I'm taking this and I'm multiplying it by 0. Of course, I get 0. Then over here, next one, I've got negative cosine squared x, and I'm multiplying by this guy over here. Multiply across this diagonal and that diagonal and subtract. So this times this is going to give me a negative 20 sine of 2x cosine of 2x. Minus a negative 20, so that's plus 20 sine of 2x cosine of 2x again. And it cancels. So we get 0 there. Now, I will say it would not have been as obvious, perhaps, if we had left this guy as negative 2 sine of x cosine of x, and then this guy as the result of the product rule that we would get from taking the derivative of something like this. But if we had chosen not to do that here, we probably would have chosen not to do that there. And because of that choice, we still would have had a similar cancellation. So I say all of that to say that your answers may look different, or these trig functions here may look different if you did not recognize that as a double angle formula for sine. Okay, last one. Got sine squared times this times this, which is 20 sine of 2x cosine of 2x. And we're subtracting a negative times a negative, so that's positive. So we're subtracting a positive number, which is going to give me a negative number. So we're saying minus 20 times sine of 2x cosine of 2x, and those reduce, and we get 0. So I have something times 0 minus something times 0 plus something times 0, which is, of course, 0, which means that the functions that we started with form a linearly independent, or linearly dependent set, excuse me. On the interval from negative infinity to infinity. Now, they use a different justification in MyLab Math. So let's look at the options in MyLab Math and talk about how we would use their options to answer this question. So these are the options in MyLab Math. And these refer back to the definition of linear independence. We say that the functions f1, f2, and f3 form a linearly independent set. Or let's say linearly dependent set, if there exists constants C1, C2, C3, not all 0, such that the following is true. C1 times F1 plus C2 times F2 plus C3 times F3 equals 0. Now, if all the constants have to be 0 in order for us to get a 0, then we say that the set of functions is linearly independent on the particular interval that we're interested in. But the idea behind linear independence and linear dependence is that one of the functions, or maybe several of the functions, are redundant. Like basically that we can get one of these functions by taking a linear combination of the other two. And with that in mind, they're giving us these two options. They're saying the functions are linearly dependent because this equation, which is just this equation with f1, f2, and f3 as the functions that were given to us, 5 cosine of 2x, cosine squared, and sine squared, because this equation has the solution C1 equals -1, C2 equals blank, and C3 equals blank. Or in other words, they're saying, okay, if C1 equals -1, we'll have -5 cosine of 2x plus C2 times cosine squared x plus C3 times sine squared x equals 0. Again, in keeping with that idea of redundancy, this is saying that for some constants, C2 and C3, if I take C2 and I multiply it by cosine squared x, and I take C3 and I multiply it by sine squared x, that's going to give me +5 times cosine of 2x. You might say to yourself, well, how is that possible? What would the constants have to be in order for this to give me cosine of 2x? And there is a trig identity that says the following. Well, actually, there are two of them. Well, there are a number of them. Cosine of 2x turns out to be equal to cosine squared x minus sine squared x. Or you may remember this from Calc 2. In Calc 2, we used power reducing formulas. We said every time we see a sine squared and we want to anti-differentiate it, but we can't because there's not a cosine, we can't do the use of, we're going to replace it with this. It turns out to be 1/2 of 1 minus cosine of double the angle. And so cosine squared is very similar, except instead of subtracting those, we add those. And so you can see that sine squared can be written in terms of a constant and cosine squared. Cosine squared can be written in terms of a constant sine squared can be written in terms of a constant and cosine of 2x, and so can cosine squared. And if you take combinations of sine squared and cosine squared, of course, if you add them together, you can get 1. You can get sort of these guys. So question is now, with these, is there some value for the constant C2 and C3 so that you would get cosine of 2x over here? Well, they told us that C1 is equal to -1. And I have 5 times this here. I think I'll just take this trig identity and multiply it by 5. So it looks like C2 would have to be 5. And C3 would have to be -5 in order for us to get a 5 cosine of 2x over there because of this identity. If you're saying to yourself, I don't remember that one, but I remember these guys, well, you could multiply both sides of this by 2, or both sides of these equations by 2, these last two equations. So we have 2 sine squared x equals 1 minus cosine of 2x. And 2 cosine squared x equals 1 plus cosine of 2x. If I'm trying to figure out what cosine of 2x is, and I am because I've got that by itself on this side, I might try to solve for that by making this sign positive and then adding them together. If I add them together right now, the cosine of 2x will cancel, and I don't want that to happen. I want a cosine of 2x in my new equation. So I'll multiply this first equation by -1, and then we'll have 2 times cosine squared x minus 2 times sine squared x equals, these guys cancel, 2 times cosine of 2x. And then if you divide everything by 2, you get that trig identity that I mentioned up here. And then if you multiply this equation by 5, you get the equation that we need to identify the C2 and C3 given the C1 that they gave us, the C1 of -1, which was over here. So when you're given these options in MyLab Math, you want to choose this one with this as your first constant and that as your second constant. So you have two options. When you're trying to determine whether the functions are linearly dependent or linearly independent, you can either use the Wronskian and show that that's either 0 or not 0. If it's 0, they're linearly dependent. If it's non-zero, they're linearly independent. We showed that they were 0, that Wronskian is 0, so they're linearly dependent. Or you can find the values of C1, C2, and C3 that make this equation true, where the C1, C2, and C3 aren't all 0 at the same time. If they all have to be 0, then the functions are linearly independent. And that can be sometimes difficult to prove that every single possible combination you put out there is not going to give you a 0, is not going to give you a 0 on that side. So therefore, C1, C2, and C3 have to be 0. So you can use this, or you can use the Wronskian, and either way, you've justified your answer. Now for our class, differential equations in the spring 2021 semester, either justification is fine. I just want to see a justification.